So it seems like a lot of the topics that we mentioned last week that we need a little extra work with involved the probability distributions. This is the normal CDF and inverse norm calculations in the calculator. The regular straightforward ones we did in chapter 2, but that's been a while back. The ones that were a little bit more complicated with the sampling distributions, both with means and proportions. And then the stuff in the middle, the chapter 6, where you have random variables. This is where you combine the means and the deviations, how that works, which also would then be used in normal calculations, or could be in some ways. So let's take a look at a couple of examples. I tried to more or less put this in chronological chapter 2, chapter 6, chapter 7 order, but some of the problems involve more than one chapter. So bear with me if it sounds like we're getting a little bit ahead and then going backwards, but really I think it's a good incorporation. This packet is a good incorporation of all the different styles of the probability distributions first semester and then the beginning of second. So first problem, you have a normal population. So we know it's normally distributed with a mean of 1,000 and a deviation of 200. The first thing I notice is that the part A is asking about 68%, and the empirical rule from that first unit, 68% of the data should be within one deviation, 95% should be within two deviations, and 99.7% should be within three deviations. So first thing I did was draw a curve out to the side, put the 1,000 that I'm given in the center, and then mark off three deviations on either side. This is especially helpful in this problem because it's very easy to add and subtract these very quickly. Didn't take me a whole lot of time. So the middle 68% was within one deviation of the mean, so that would be between 800 and 1,200 or 1,200. Based on this scale. So there's my answer. Now notice 400 to 1,600 is also nice and evenly three deviations on either side, so same number of deviations. If they weren't the same number of deviations, so for instance, if it said between 800 and 1,600, we did talk about back in that first chapter how you could break down each section. For instance, if 68 is these two sections together, I could break them up into 34 and 34. But to be honest, at this point, when you're trying to do these calculations quickly, if it was something that was asymmetric, so between 800 and 1,600, for instance, it would probably be easier just to use normal CDF. But no, that's where those values come from. 400 to 1,600, though, especially since I already have my curve, I can see that's three deviations on either side, so about 99.7% of my data. Now notice the next one, starting with the next one, I have values that are not nice 1 or 2 or 3 deviations on either side. In fact, the fact that it's just one-sided tells me that either doing the z-score formula and table A or normal CDF would be the better option. Now on all of these, I have the normal CDFs worked out just because that I feel like is the most quick and efficient way of doing it. And it seems to be the preference of you all first semester was to do it with the calculator way. So greater than 1,050 would be between 1,050 and positive infinity, which we write as 1e99, between 1,000 with a mean of 1,000 and a deviation of 200. Don't forget on AP test you want to label that if that was a free response. But if it was just for practice like this or for a multiple choice, of course that wouldn't be necessary. So we get about 40% of our data is 1,050. With continuous distributions like the normal curve, 1,000 greater than 1,050 would give you the same answer as greater than or equal to. Okay, not true for discrete, but for continuous, meaning that, for instance, decimals are possible. So 1,050, 0.1 or 0.001 would be possible. In other words, fractions of decimals. Then there is no difference between greater than versus greater than or equal to. 0.4013 would be the probability in either case. The next one we have less than or equal to, more specifically 960. So this is going off to the left. Draw yourself a curve or figure out where about 960 would be. Remember, area to the left would be between negative infinity and that value with the mean and the deviation given. So I got about 42% chance or probability. Between 960 and 1,050, so that gives me both my lower and upper bound. I have no need for infinities with the mean and the deviation, so I get about a 17.8% chance. Okay? I went out 4 decimal places because that's about the same that you would get from the table A. There is no hard and fast rule in terms of how many decimal places you have to go out. Since we're talking about probabilities, which could be written as percents, I would go out at least 3. So this would be the same thing as 40.1%, for instance. And that hopefully will help stay consistent with those of you that have had or are currently in calculus as well. I think 3 is the usual. Now F and G are going in the opposite direction. So now instead of looking for the percent, I have given the percentile, which just keep in mind is a percent to the left of that mystery value, and I'm looking for what that mystery value is. So instead of normal CDF, I'm going to use inverse norm. Inverse, think the reverse. I'm working backwards. So 90th percentile, I use 0.9, so there's my percentile written as a decimal with the mean and the deviation. And I'm told if I have a distribution with a mean of 1,000 and a deviation of 200, that a score of 1,256.3 would be the marker or the benchmark for the 90th percentile. Anybody who got above that would be above the 90th percentile. Be careful here, top 5%, the percentile that goes here is always, percentile by definition is the percent to the left. So if it's top 5% or top 10%, you need to subtract that value from 100. So top 5% in this case would be the same thing as the 95th percentile. That's the value that goes in here. That would be equivalent to a score of 1,328.9 or higher. Multiple choice example, you have a little bit more of a theoretical one, not an exact value needed to be calculated. I drew a visual once again to kind of illustrate it for myself. I have 30 in the middle, deviation of 4. I'm looking for what the equivalent probability of greater than or equal to 0.26. Sorry, not 0.26, x greater than 26. I just got thrown off a little bit because as I'm reading it, I realize I've shaded in the wrong way. So greater than 26 would actually be everything over here. So then what other area of that curve would be equivalent to that? Now looking at these numbers, I see lots of 26s and 34s. So why would 34 be mentioned? Okay, 34 would be mentioned because it's the equivalent distance in the opposite direction. So if greater than 26 would be this whole area that I tried to squiggle in black here, then the equivalent area involving 34 would be 34 or less. So let's see what we have. That would be the complement, that would be in between, that's not going to work. So the correct answer must be A, keeping in mind that less than 34 would be the same thing as less than or equal to 34. So that's why I'm getting that answer. So ignore E, that should be A. Okay. Starting on the next one, we're going to look at distributions, combining distributions. So this is the Chapter 6 material. We will be doing a lot more with normal CDF in other applications, so I didn't put too much Chapter 2 stuff on here. Okay, so number 3, you have the distribution of heights is 68 inches with a variance of 1.52. Notice, underline variance. Usually we're not given variance, we're given deviation, but think back to the relationship between that. Variance is just deviation squared. And the distribution of female high school students has a mean of 66 and a variance of 1.64. If the heights of male and female students are independent, what is the standard deviation of the difference in their heights? Okay, so the independent part is important. If we did not know that they were independent, we would not be able to calculate the deviation or the variance. We could still combine the means, but not the variances or deviation. So with deviation, we actually do have to work in terms of variance. So the fact that it's given in variance does help us. The variance of the difference, males versus females, would be equal to the variance of males plus the variance of females. So this is not one of the formulas on your formula sheet. Be careful here. Even though I'm finding the difference, I would add the variances. So I don't have to do anything to 1.52 and 1.64 other than add them together because they were already in terms of variance. That gives me a combined variance of 3.16. And then take the square root of that to find the deviation, and I get 1.777, which would give me 1.78. D as the answer. Okay, the next one you have a chart of horse names. I hope that was seasonally appropriate. Specifically, we're going to focus on the horse name Night Sky. What's the probability that Night Sky can run a quarter mile in under 24.5 seconds? Okay, so because we have the information that does follow the normal model, we can use normal CDF. So under 24.5 seconds would be between negative infinity or 24.5. You could use a more realistic lower bound like 0. There's no way it can finish faster than 0 seconds. But just to stay consistent, I use negative infinity. And then the deviation of night sky, him or herself, is 26.8 with, mean 26.8 and deviation of 1.9 is given. Plug that into the calculator and I get 11.3% chance that a night sky would finish the quarter mile in under that time. And now the next one suggests that night sky is going to run 12 of these races. How likely is it that the horse runs under that time limit in 5 of those races? So now be careful. This happens sometimes in AP free response. It doesn't specifically say, now we're talking about a binomial, but now I'm looking at a certain number of races. I have a probability of success that I've just calculated. This has happened several times on AP free responses. And I want to know how likely it is that this X random variable value occurs out of those total number of trials. So therefore you have a binomial distribution where you have 12 trials and an 11.3% chance of success. Therefore, the probability that night sky runs under 24.5 seconds in exactly 5 of those races, X equals 5, would be binom PDF 12, 0.113, 5, and I get a little less than a 1% chance, so 0.0063 as the probability that occurs. Okay. Part C of this problem, so this kind of ties a whole lot of Chapter 6 together. If the horses are independent and they are running a relay race, how likely is it, what is the mean and deviation of the combined relay team score? So the mean team score, keep in mind, or time, I should say, is, since they're doing a relay, only one horse is running at a time. The mean for the team would just be the means of each individual horse. So you're going to add up the means for all 4 horses given in the chart. So you get a mean team score or team time of 126.5 seconds. The deviations are also given, but keep in mind we can't work with deviations. We have to work with variances. So I'm going to find the variance of each of the 4 horses. So square the values that I'm given, add those together, get 29.48, and then take the square root of the 29.48 to get the deviation for the team score. And both of these are in terms of seconds if you would like to include units on that. Okay, one more for this first video here. So for this first test, you have a class average of 80 with a standard deviation of 10. For the second test, the class average was 70 with a standard deviation of 12. Ignore that. That was something that's not needed. What's the average for the 2 tests added together? So mu of 1 plus 2 would just be the sum of the means. Okay. What is standard deviation for the 2 tests added together? There really should be something written here that the tests should be independent of one another. It's not, but we have to be able to do this to do the rest of the problem. So issue with the problem wording, but know that it should say independence. So we have to work in variances once again. So the standard deviation, or now the variance for the 2 tests added together would be the variance of the first plus the variance of the second. And then to find the deviation, take the square root of that value, you get 15.6. What's the probability that the sum of the test scores is less than 140? So because we're assuming a normal distribution, which should have also been stated in the prompt, we would do normal CDF of 140 or less with the mean and the deviation we just calculated to get a probability of about 26%, just a little over 26%. What is the difference in the test scores? So 80 minus 70. I subtracted them in the order they were given in the problem because there was no indication to do it otherwise. So I got a difference of 10. Subtracting it the other way would have been fine as long as you indicate it. Don't just put negative 10, but show where that negative 10 came from. Notice that the deviation, because even though I'm finding the variance of the difference, I'm still adding. So part B and part E end up being the same value. And then find the probability. Do the same thing with normal CDF. Last little bit, if I cut the test scores in half and add 50, it would affect the mean, so half of the mean of the original plus 50, only half the deviation, you would not add 50 on that one on H.